Hello.
Hi, Alex. Good
Hi,
to see
Michael.
you.
Good to see you as well. How was your weekend?
It was actually quite quiet. I've met a friend. We took a walk in a park, and otherwise lots of reading. I finished actually really good book, Apollo Murders,
Full of
Chris
murders.
Hadfield. So I really enjoyed that one. I had watched For All Mankind before, the TV
Hmm.
series, which is also like Apollo astronauts and things like that, and US Russia kind of run to the moon.
Yeah.
And so I got this. I ordered that before Christmas because I wanted to have a signed copy from Chris Hadfield. So that's really
Ah,
cool. And it's
fancy
really
signature.
really good read. It's a really good read. So I can imagine. I can recommend that book.
Okay,
It's
cool.
very fast-paced crime story and space. And what's cool about this one is actually that because he's an astronaut himself, he has like
Mhm.
lots of detail that you would otherwise probably not find easily in a book like this, which was quite cool as
Mhm.
such. So that was mostly it on the weekend.
Sounds,
How about
sounds
for
good.
you?
For me, it was a mix. So I had a quiet yesterday, not doing much, but on the weekend, on the Saturday and the Friday, I went to the to Bohemian Forest, so Bayerischer Wald in German. That's
Mm,
east of Munich, and that's like a middle mountainous area where you can go cross country skiing or Nordic skiing. That's
mm,
what I do. That's what I did, and it was very nice because there are not so many people around. So
yeah,
I had
I can
I
imagine.
had
Yeah, the
nature,
weather here is
forest.
actually switching around between sun, rain, and snow-ish and storm every 5 minutes, basically,
Yeah,
because
here. Yeah,
the high wind speeds, it's kind of pushing the clouds through in a really
yeah.
quick frequency. So it's very changes like all the time. So
Yeah, that's the
yeah,
same here. It's very stormy. All right.
cool. Let's
Cool.
get started.
Let's get started. Exactly. Thank you for watching, and thank you for joining this Discover Neo4j AuraDB session with Michael and myself. Um, when you watch this live in chat, please let us know where you watch this from. This is a cool addition this week, I think, with
Yep, totally.
the Wordle hype. Let me share my screen quickly and let's
Wordle
go.
edition.
Yeah, you even printed it out. Very cool. Let me do that, and here we go. I guess if you watch this a couple of times, you know what's coming. But before I go into the detail, here is our call for papers is now open. We'll post a link in chat in a second. But if you are interested in presenting something about graphs to the wider graph community, then please submit your suggestion. We're looking forward to hearing from you for that one for sure. Here we go with the plan. So go with a quick recap. I'll do that in a second. What we do usually is today is going to be a little bit different, but yeah, we
Yep.
pick a data set. We got a data. If you have a data set that you are like us to explore, please let us know on the channels. Pick anything: Twitter, Discord, community forums, anywhere really. If emails, if you got them, we can be looking forward to hear from you about this, and then we think about kind of question we might ask. I mean, this again, like I said, is a little bit different this week. Determine a data model loading query. What is Neo4j AuraDB free? Just quickly, it's the free version of Neo4j AuraDB, which you can access if you go to this link. I'll also put that in chat in a second. And then you can subscribe or register for a AuraDB free instance, which is free. So you get this, and what you get is a graph database as a service in the cloud, which is limited to 50,000 nodes and 175,000 relationships. So some limitation, but it's big enough for a test run and for explorational projects, I think. And I guess we showed this here in the series that we had not a huge problem with data limitations here for the purpose of exploring a little bit what graphs and AuraDB can do for you. You have access to Neo4j Bloom, which is our visualization tool, as well as Neo4j Browser, which you'll see in a second. It's free forever, so you keep it, you have it. You don't have to worry about it being deleted or closed down. Yeah, if you want it, go to this landing page, and the link will be in chat in a second afterwards. So you can give it a spin yourselves. Let's get going. So today, Wordle. If you have living under a rock and you don't know what Wordle is,
Like me. I just mostly saw it by people posting their Wordle things on Twitter, actually. I had not played it myself, to be honest. But my wife has been playing Wordle.
yeah, I think it's kind of like blew up a little bit over the last couple of weeks, or since end of 2021 for sure. I checked it out
Yep.
I played a couple of games. There are now Wordle derivatives and all kinds of things. I recently discovered there's a Wordle, so that means you get a map, like a outline of a country, and you have to figure out what kind of country that is
Okay.
in 5 or 6 guesses. So then all kind of things. There is in all kind of languages now: Hungarian, Icelandic, Turkish, Spanish, Filipino, Dutch, German, whatever you like. So there are various versions. Seems to be there's a Klingon version as well. I'm not sure,
Nicole.
but my Klingon is not very good. So we're gonna play English,
Yeah.
and this is how it looks like. So basically, you get you have 5 fields or 5 boxes
Letters, kind of,
or
yeah.
letters, which you can type any word in the English language here, which has five words. It has to have 5 words, and then it tells you. I think here it shows a little bit. Tells you if you have a word, a box, a letter guessed correctly in the right field, then it's getting a green background, and if you have correctly guessed the letter, but it's on the wrong place, then you get a yellow outline or yellow filled in box. And then if you have guessed a letter and that is not correct, it's not in the word we are looking for, then it's just gray. So you don't know. If so, you just know that this word is not available in this word we are looking for today. So this is the game, basically. Very easy, if you think of it, but very difficult at the same time, because you have to come up with a word that's 5 letters and works with the hints you get. And you have 6 guesses. So that's maybe another thing. If you after 6, if you don't know the word by the 6th,
Game over.
it's game over for you or for us, because we play this now. So we will see how that goes.
Yeah. So you have tips for starting words. I mean, as starting words, you want to choose something that kind of covers a lot of different letters and most frequent letters probably as well. So that are very likely to come in. And I guess every Wordle player has their own secret starting word or something like that they use all the time. And so if you have any suggestions, let us know in the chat. Otherwise, Alex and I make something up
Yeah. So
that fits.
like you said, it's a world that has lots of vocals, is usually kind of helpful, because then you kind of get a few
Yeah.
things. I have my starting word, so maybe I'll start with this one, which I use house. Covers OU and E, which is quite helpful. It covers an
And
S,
S
which
is
is
also
also
frequent, yeah.
so very helpful. So it's maybe not. Yeah, there. I read a guide the other week about what perfect word to use. House was not in there, but I'm sticking with house because I like it.
Okay, let's try that.
Okay, there we go. And all right, well, that's so good this
Okay,
round.
the E is good. Okay.
It's good. Yeah.
So, so the S is not in there, right? So it's probably something, perhaps an R somewhere.
Yeah.
And then, what do we have, like river or so? But that's the double R. That's not so good, right?
Yeah.
Perhaps diver, perhaps?
If it could be one, yeah. We just double checking. We have another I, so we don't know. Yeah. Shall we try diver?
Sure.
Okay. Oh, nice. Okay, good. We have correctly guessed the ER at the end, so we know it's something ER. and we also know the D is in there, which
Mm-hmm.
which we didn't know before. So we have now
But in the wrong position, right? So it's
exactly it's in the wrong position. So something ER. So maybe
But the D is in the wrong, then probably with
the
DER at the end, right? So because the second letter is often not like,
yeah,
it's
you could do
very
like
unlikely that's a D,
yeah. So
right?
sometimes
So,
like this, but the E is not there. So it could be an A. Could
adder
be
with double D, but I'm not sure
yeah.
if
Could
something like this.
technically work. Yeah, for example.
Yeah. What else could be? Hey, John, Karina, Patrick, if you have suggestions, feel free to chime in.
Exactly. Let us know if you have any ideas.
Ladder has too many characters, right? LADDER is one too
Yeah,
much, right?
letter does not work.
Uh,
Later would work. Oh, then we
but
don't have the
then we don't
D.
have the D anymore.
Yeah, true.
Okay. What else could we use?
Wider could work. Oh, this is the E and the I we don't have. We already
Yeah.
said that the I is not working.
Wonder? No, we already had the O, right?
Yeah, the
And it's
O is
also too
also
long. We don't have an I, so
Elder from Santiago.
okay, let's try that.
Then we have two E's, but that technically works. The L we didn't have before. Must have an A, says John. Why do you think it must have an A, John?
Good question. I think it's permitted that you have twice an character, right? Older
Yeah, we
can't be Narine because the O is already in the first. And Rider could also not be because the I is not correct.
exactly. The I was already ruled out. Wonder
Wonder
technically would
not work because it's one character too much. It's
it's
6
too
characters.
long. So shall we try Elder? I think
Yeah,
Elder
let's
is.
try Elder. It was. Oh,
Ooh,
cool!
very nice.
Good job. Thank you,
Just playing this
Santiago.
for the first time on this machine here, but on this instance, yeah.
Nice. Good
Wow,
one.
very nice, Santiago and Elder. This was the correct guess.
Super. So
two
that's how it
two
works.
E's. Yeah, exactly. So we have this is some, this is what
It's a
can we
little
have?
bit tricky, the two E's, right? So that was not
Two E's a
obvious,
little
right?
bit tricky. Yes. Yeah. Yeah.
Patrick, because we wanted to just play the game for real, basically,
Well,
and we want
Santiago
to solve
played
it
this
actually with
morning.
Neo4j
Uh,
later.
well, obviously, it's the same word. It's the
Oh,
same word for
Santiago
everybody.
played before. Okay.
It's a little bit of cheating, Santiago. I think you. But all right. Let's. But yeah, okay. No, what we now gonna do is we tell you or show you how you can do this in Neo4j without having Santiago fill it in before you are already playing it, because you probably won't have the possibility to call him up and say, "Hey, can you can you let me know what the solution is?"
Yeah.
Um,
Okay, we had house, diver, and elder. So perhaps we can try to reproduce this in Neo4j and then see
yeah,
what kind of suggestions we get from there as such.
yeah.
Right?
I can keep this open and we can have
Yeah,
a look
so
at
if
it
I
later.
forget the words, then you can remind us what
Yep.
it was. Super. And so without further ado, let's perhaps have a look on how we get this into a graph and then how to get going from there. Right?
Yep.
So I'll share my screen as well. Let me do this. Cool. So our colleagues actually in Creative put something together with some graph terms actually, which kind of spells out Neo4j at the end,
Yep.
which is not
It's
100%
not
legible
correct though,
because
and
the 4 is in there and the O from Bloom already should have been green up here.
that's
Right?
true. Yeah.
But it's still fun that like all these graph terms have five characters, right? So anyway, so I put together I started with an GitHub gist, but then I put it into a repo. But we also put it into the Discover Aura free repository. So I'll just paste this really quickly in here so you can follow along. So I thought, last week Wordle was sold to the New York Times for probably single-digit $1 million, which I really like for the creator actually of the game. So I think it's a win-win for everyone as such. So he got some money for a fun creation. People can continue to play it. He doesn't have to take care of like maintenance and running servers and like all the other stuff. And
Yeah.
so from that perspective, I think it's a win-win. But I thought actually it would be interesting fun. How would you represent something like Wordle in a graph, right? So I looked a little bit for the data because I wanted to get a list of words from somewhere. So I found this repository of an solver in R, which basically has like an R solution, and it has this list of words here, right? So all the words from ahead all the way to Simic, basically, right?
Oh, wow. Okay.
So, and I basically took this, turned it into a CSV. I put it also the CSV here in the repository, so I can use it there. And now we can basically load it from this URL and create words from that. So that's kind of step one, right?
Mm-hmm.
And then the question is, how do we model the data so that we can use it as a graph? Right? So before we do this, we can go to Neo4j Aura, create a new AuraDB free instance. So we click on create database, select AuraDB free. We can call it Wordle. I can pick Belgium as a database here, and then I just call it Wordle 2 because I already have one Wordle instance. And then you can say click create database. Don't forget to save the password here because that's important because you need this later on. So click on the copy icon, save it somewhere save. Then click continue after you check the box. And then basically you're good to go in 2 minutes or so, right? So, and while you're waiting for your Aura instance to spin up, if you don't have one yet, we'll look a little bit at the first steps in the model. So I thought initially I went with a more complex model. So let me just remove this. So I basically have this word. For instance, arrow is a word in there, right? So I have a word node in here, which is everything that I have. And my initial model looked something like this, that I had something that I called character at position, which had actually two properties. So which had one property index, which was like 0, 1, 2. And then a second one that was character, which would be A for the first position of arrow, right? And then I had here an has relationship. And then I also created a second relationship here in this one, which is basically start or starts. So we know which character the word starts with also just from the relationship. And then I thought actually what we can do is we can create this chained list of characters, right? So I can actually, I think, can I drag this out? Oh no, I can, oops, sorry. I can duplicate this one and remove this dot. So, let me draw it out so it's not as confusing. So I have my second character basically, which is an R. So I use char at pos again. Have my properties again named index is 1 this time, and character is R, right? And my
Why did you put the
relationship.
starts relationship? Because with the index, you already know that 0 is
Yeah, I just thought perhaps there's a good kind of graph pattern that we can just express the word starting and then, because basically what I also did in the first model that I created, I had added this next relationship basically as well.
okay.
Right? So I kind of wanted to express this as a graph pattern as well without actually using the numbers, where I just say word starts and then next basically as such. Right? So and this is basically how I continued here. So I had basically, oops, this was a little bit too much. So in arrow, you can actually use Command D for duplicate. a node and all its relationships, which is really nice. So this is our index 2. Then we do command D as well again. And then we have index 3. So starting at 0, right? So this is now an O. And then we press command D again. And this is our last one, basically index 4. And character W, right? So this is one model that we could use as such, right?
Yep.
The other thing, so this is kind of what I started with, and then I played a little bit around with it. There's another option, a second model that we could use, which is simpler. And so I started with this model, and then I also thought about this second model. So for instance, if I have a second word, we could also do something where we just point to the characters. So what's particular about this model, of these char at post nodes, we have actually more than 26, right? So because we create a certain position, right? So it's basically not just 26 nodes, but 26 times 5 actually, right? So we have each character. No, it's to the power of 5 or something like that, right? So anyway, it's I think times 26 times 5, right? So for each position we have one character. So we span up the square basically, or the rectangle. So that's kind of this model. And then I had this other model where I basically just said I used the characters again. So let's say we use a different word here called, let's say, crash. And then I just put the number on the relationship. So I just said pos 0 of this one. So I put it into the relationship type actually. And then basically the other ones are just pos 1, pos 2, and so on, right? So I basically called this one pos 1. And then it's the character R and so on, right? So so that is the second model. There's actually also a third model where we can just say we put actually the index not into the relationship type, but into the relationship itself. That's something that I haven't done yet, but that might be even better as a model as such. But kind of playing around with the different models as such. Okay, so now our Aura instance is provisioned. So if we click continue here, our Wordle 2 is running. And so we can use this. And I already got my Neo4j browser open here from my database. And we can now load the data. And in the repository, actually, I have a bunch of load scripts that we can look at. So first, we can create a bunch of indexes for words and for the character at position. Basically just that we have uniqueness on the name or on the index and character as such. So that's something that we can just paste in, and it would create these two constraints. And then the other thing that we want to do is load our words, right? So if you do this, it loads basically and creates 12,900. So 13,000 words are in the CSV file, right? And now we have a bunch of words in our graph. And you see those as such, right? A lot of these words are really kind of, I wouldn't even
obscure. Very
baker,
obscure.
I don't even know what
I don't know what that
right?
is.
Or RT or whatever, right? So there's kind of interesting words.
Yeah.
But they must come somewhere from a dictionary, right? So
I guess so, yeah.
So so that's kind of our words that we can start with, right? And then what we can do in Neo4j itself is we can use the strings on the word. So let's show 10 random words here. What we can use return the string of the word. Sorry, n dot name. Okay, n dot name. Right. So this is kind of
the list.
Our word in here. And what we now can do is we can also split this as well. So we can split this n dot name on empty string. And then we have characters, right? So we see each of them gets a list of characters. And this is what we can do to build up our model, right? So we use this list of characters for each word to build up our models as such. Cool. And if we want to, we can start with the simpler model actually first, because that might be easier to understand, because that's super simple, basically spelling out exactly what you do, right? So you take the word, split the name as we just did here, and then for each of these characters, I just manually put in the relationship from the word to each of the characters as such.
So each word becomes a little graph with
Exactly. And that's what we can look at. So we can just run this. It creates, I think, 60,000 or so relationships, 64,000 relationships. So that's 12,000 words times 5 characters, right? And so it creates, but it only creates 26 nodes, right? So each of those character nodes is a proper supernode, right? So because each of those points to, 5,000 words or something like that, or 6,000 words as such. Which actually is a good point that I wanted to look at, which is basically, we talked in the beginning about this kind of frequency of characters, which characters are how frequent in the data, right? So that's actually something we can look at in the graph, where we can say, okay, let's find these characters and return the char and the size of the or the number of incoming relationships, right? So these characters have incoming relationships basically, and we call this degree in graph terms. Or we could also call it frequency, basically. How often did this character appear in any word, right? Mm-hmm. And then we can order this by frequency, descending, and return this. Because it's only 26 characters in total, we get 26 rows back ordered by how frequently they appear, right?
Yeah.
So, and if you look at this data, we can also switch to this text-based view, which might be a little bit easier to read. So we see like characters like S, E, A have 6,000-ish occurrences, right? And then it goes down to the 4,000s, which is then O, R, I. Actually, I was surprised that L was so high.
L is
I would have thought that T is actually much higher in the list, and N probably as well. But probably because I come from German, so a different language.
Different. This is different.
More in my brain, right?
Yeah,
For instance, in German, Y would never be so
no,
high up here, right? So like in English.
A few lonely words.
And then towards the end, there's Z or C, J, X, and Q, which are kind of expected. Although I think, for instance, in German, Z might be actually also higher than, so it might actually even flip positions with Y, or the J could be because it's also more frequently used, right? So, but that kind of gives us the frequencies of characters as such.
So my starting word isn't all that bad, but the age is a little bit on the
the age is a little bit down here.
Yeah,
right?
it's
so
only
1700. So imagine we had a Jupyter notebook. We could also plot this as a chart basically, and get a distribution basically by characters as well. But what I then wanted to see actually is, let me find this. I put this somewhere here in my cheat sheet. I wanted to actually see, I found it. So if you look at each word, right? So we find each word and the characters that are in this word, right? So this is kind of gives us, actually, let's take an example, right? So if you, for instance, take today's word like elder and return everything, so we can just assign this whole thing to a path and then return the path as such, right? Mm-hmm. So this would look like this. This is our little elder graph, right? And you see that actually E appears twice in position 0 and position 3, and then we have the other characters as well, right? Yep. And so if you take your word house, it would look like this, right? Or if you use, what do we have diver, it looks like this. So each of those forms a little graph, right? Mm-hmm. So, and we look into solvers and stuff like this later, but just to show you, give you an understanding or an idea of what these things look like. What we can actually also do is we could also look at which words or which characters actually shared by two words, right? So if you had our second word, like let's say elder and diver, our two last words basically in our guessing. Oops. Elder. Did I misspell anything? I think it could be because the relationship is already used up from one direction, so we just do it in 2 parts. And then pass to what? Word name diver and word name elder. Why does it not?
You didn't specify a relationship, but that does not matter, right?
No, actually I don't want this, right? So because I want to have all the characters. So let's do this again. So if I do this works. If I do elder, it also works. Why does this not? So if you connect result nodes, then it automatically connects them. Okay. And so if you do a second match, that just goes from this character. Oh, I remember. I know why. Because I use W twice. That's it has to be W2 or nothing, because you have to actually the path variable.
Yes. Okay. Yeah.
So this is actually much better, right? So we have over here we have elder, and here we have diver, and so we see what are the shared characters basically between the two, and then we could also return the characters, the other characters that are in these words, right? So basically we could say C3 and let's see, or C1 and C2 or something like that, right? So when you also want to see the other characters of these words, then we would see here elder has the L extra and diver has the I and the V extra as such.
Yep.
Right? So this is just a little bit kind of exploring what the graph model basically looks like from that perspective. Let me take a screenshot of this one, because it's probably nice for the blog post as well. Okay, so this is kind of just the graph model bit. What I actually wanted to look at is kind of how can we find better starting words as such, right?
Yeah.
And so what we do is actually we find our word, and then the characters that this word is containing. And then we basically can say for this word, we return the actual text of the word, and we just sum up the frequency of the character. So for each character that's in the word, we sum the size of the number of relationships of this character. Right. So we have this is the number that we just had with each of the letters, basically. Right. It's kind of the total frequency. And then we order this by total descending limit 20 or something like that, right? So this would give us nothing, because it's name actually here, not word. Right. So, and now we see
of course, yeah, good.
right, lots of S and E and
Yeah.
so, but that's kind of also not what we want, because we don't want to have duplicates in our starting words, right? So we don't want to have double characters in our words here, right?
Yep.
Which would
That's
be not
true.
so nice. So what we could do here actually is to say we count distinct characters. So, and if I have only 3 distinct, like here, we have only 3 distinct characters, then this is 3, and only if there's really 5 distinct characters, then it is 5. So we can actually say when this is equal 5,
Okay.
as this, or unique. So this would give us false, true, basically for each of these rows. Is this unique or are these not unique?
Okay.
And then we can use a trick, because we can also sort by Boolean stuff as well. So we just say sort by unique descending, I think is the right order. I think. So, and this gives us now where unique is true, where this expression is kind of true, and then the count. So they are not as high as the other ones,
No.
but they're still pretty high. And I think arose was also the one that you had on the Wikipedia page as like a starting word as well. Right? Or race is probably another one that's nice.
Yeah.
Laser. Right. So these are some that you could see are basically unique. Right.
Yeah.
And now what we
No,
could
that makes
do
sense. Yeah.
on top of this, we could actually return only ones that have unique. So if you sort them, basically these characters, if that is unique, basically, right? So that then we could say, okay, give us the ones that have unique sets of characters, right? So we could say, how could we do this? We take the name or the word, and then let's say limit 1000, and then we return epoch, or we just do epoch call sort. So we sort a list of the split of the W of the word, basically. So we have a list of characters that we sort, and then we can basically max total, and then this should give us where unique, and then with star order by total descending. Okay, let's see what happens. So, and we can probably use collect word 0. So like the first entry of all these words that share one set of characters, basically we just take the first one, basically of that one. Right. So, and then we have for each of these combinations, we have one entry, right? Tiers is a nice one, right? There's an S and a T and an R and an E and an A. That's pretty. Or Ians is also a nice one.
Yeah.
Right? So this doesn't use so much the graph aspect of it as basically aggregation functions, custom procedures, split text functions, and stuff like that. So that's more like demonstration of aggregation and custom functions here. Right?
Also important.
Yeah, which is also really important. But there's some nice ones in here. So tiers, I really like tiers and laser actually, and IL, nice.
Laser tears.
Laser tiers. Years is also in there. Interesting.
Years, yeah.
Because
very high up. Yeah.
the
Y
Y,
if you wouldn't have guessed. I mean,
yeah, nice.
Yeah.
So there's some good stuff in here. So we should probably remember that as well. So let's take another screenshot of this one
for next time.
For next time. I also save the history at the end, so we can put it in the blog post. But now what we actually wanted to do is kind of a solver, right? So how can we kind of express what we put in, what we've seen, and what we can basically do about this, right? So if you take a word like what I had here, like crash or so, and imagine we would know that we have a C and the H correctly, how many other words do we have basically that we can find in our graph as such? Right? So which we can actually just express as a graph pattern, right? So that's what's kind of one of my goals, that we can say we have the C at the beginning, which is pos 0 of our word, and then at the end is pos 4 is our character C4, which is H. Right? And then we just return basically how many C0, which words basically do fit with this as such, right? So let's see, it doesn't say H is not, because H is of course in character. So there's a bunch of, how many are there actually? Table 23, right? So this is basically something where we know, okay, we know these two characters, but then we could say, imagine we had thought, or we had put in, let's say cloth, which doesn't share anything else with crash, right? we could also say that L, O, and T are actually not in the word, right?
Mhm.
So that's an additional information that we have because we know which characters were gray, right? Right. So where we can say where not exists, and then we just can put in the pattern W any position, right? So because we don't know which position, and we say we don't have any. What did we say? L,
and it doesn't matter really because we just say, okay, this character is not in.
right?
Yeah.
And then the other ones we just end together, right? So where not exists this, and not exists the O, and not exists the
T.
T, right? So this would be like cloth, right? Where the C is correct and the H is correct, basically, right? And the other two were gray.
Yep.
Other three were gray, right? So so we had 23 before, and now we get, how many are these? 7. 7 is already much better, right? So we could now kind of pick one of those and say, okay, what, for instance, if we used something like church, right? So, I mean, church is not so good because we know that the C is already there. So we could,
church,
for instance, use crush, for instance, right? So if you said, okay, we use crush, then the R would be correct, right?
Yeah, would be
at the correct
yes.
position. So we can actually add this to our match. It would say at position 2. At position 2, there would be an R, which is green, and the S would also be correct, right? Yeah. On position 3, this is then C2, C3, and that's the S, right? So we have not the others, and we know that the U is wrong, right? As well.
Mm-hmm.
Right. So, and then I mistyped something somewhere.
Do you need a comma after the match, the first match?
Exactly. So, and it doesn't find anything. Why doesn't it find anything? Did I again do one of these kind of weird misspellings? +3. C3, C0, C2, C4. No, sorry. It's the R is at +1. See? Right? And then.
Yeah, crash, of course. Yes.
And then crash is the only one that's remaining, basically.
Right?
Yeah. So this is how we can basically build a manual solver as such. And then if you wanted to automate this, then we would basically move all this kind of information into an input thing, and then use a dynamic expression to use this as a solver. So in this one, it wouldn't be as easy because I would basically need to say, I would have to construct these relationship types dynamically, which is not supported. So you would actually also, you would probably also store it on the relationships themselves, right? So what we can do really quickly is basically find all +0 relationships R and set R dot index is 0. Find all +1 relationships, all +2 relationships, all +3 relationships, and I hope I don't mistype anything. Right. So now all our relationships also have a position attribute. And now we basically can say, okay, can we somehow take this information, which characters are correct, which characters are incorrect, and turn this into something like an expression, right? And I played around with this a little bit earlier. Here. So we could have something like this, where we say, we had just turn our word into a list of maps or dictionaries where we have each character and then say, is this a match? Is this not a match? And if it's missing, then it's the character's there, but the correct position is not there, right? So it's basically
yeah, okay. So yours Kali H. That's not a word. Okay, so you just you know that these, or was it a
Actually,
word?
I think it was even a
Kali?
word. Let's see.
Or maybe
What
that's
kind
what, I
of
don't
word?
know. That's a different story.
No. Okay, I
Okay.
just made it up, I guess. Yeah. But
Okay, good.
anyway, so think, but you can imagine that this is kind of the word is here. It's basically C is correct, A is also correct, but if you don't know where, then L is basically not correct. The I is also not correct, and the H is also correct. Something like this. If you were to spell this out like this, right? So this is
Okay. So
green,
yeah,
green,
okay.
yellow, and gray, right? And then we can take this input, and for each word that we find, we actually create a dynamic, more or less dynamic expression where we say, for each word, go over this list and check basically for each character based on its match attribute. Does this relationship exist? Does this relationship not exist? Or do we not know where this relationship is? Right.
Mhm.
So, and how we can do this? We can do this with a subquery. So we have our word and our input, which is this attribute here. And then we go over the, we go over the all the attributes of the input. So we create an index from 0 to size of input -1. This is our index that goes from 0 to 4, basically. And then we can shortcut our stuff a little bit, where we say we want to have the total size of our input, which is 5 in this case. We want to have the index, our word. The M stands for input.match, so that's kind of true, false, or null, and our character. That's just that I don't have to type so much. And then we basically express this as a conditional, where we say, is this one? I think this one here. So where we basically say, if this is true, then this relationship has to exist. So we say index to this character. So you see that I tried this with the other model. So we'll just switch this over to this model. Mm-hmm. So when this exists, then at this index, there needs to be a character with this character. When it doesn't exist, then in general, we don't want to have this character, right?
Yep.
And when we don't know if it exists or where the position, then we want to have also just the existence of this character, basically, right? So only if it's green, basically, then we know that at this index there must be this character. When this is false, then we don't want to have this character at all in our word. And when this is null, then we just don't know the position. So we say the character exists basically in this pattern, right? Mm-hmm. And then there's a little bit of a trick that we had to do, which is basically we need to see did this actually return true for all 5 indexes, basically. So what I did as a trick here is we take our total, which is kind of the size of our input, our 5, and count star. So how many rows did this produce? So if it's true, if these expressions are true for all 5 rows, then this count star would be 5. And then we say where count equals total. So if we have 5 out of 5, basically, then our subquery returns some random value, which basically says it returns 1 row. And then if this is true, then our word is basically found, right? And so basically based on this, we can now say, let's run this. And it takes a while because it's a kind of a brute force approach, right? But if you look at this, so we see the C matches, the H needs to match, and there needs to be an A somewhere. And so we got 4 results back, right? Including our crash. So if we now said, okay, for instance, we would say the A is at position, we would move the A position to somewhere else here, up here, then we could actually get more, right? So, and then you could also even input your subsequent rows as input. So you have like rows of 5 twice or 3 times, and then it could compute the ever smaller growing set basically for these words, right? So, and so only the initial one with the 12,000 ones is a brute force because it has to check 12,000 times 5 basically in all these relationships. So that's a little bit of a brute force, but it's not too bad. I mean, there's some optimizations that we could do still here, but it's just demonstrating that this is a generic, basically incremental solver in Cypher. Right.
Yeah.
So that's pretty neat. And so
mean,
for the other,
yeah,
sorry, go
I
ahead.
mean, with this, I mean, if imagine this was your first guess, and you get 4. Obviously, it was a little bit, but I guess you would maybe start with one of the ones laser or something. Then you would get a couple of words, and then you can expand on it.
Yeah, exactly. So let's imagine we had laser, right? So we had L, the A is correct. Then let's say the S is not correct. And then the E would also be correct. And then we have the R, which where we don't know where it is or something like that, right?
Mm-hmm.
Right. So we have actually lots of matches. Or let's say the R is also wrong, right? So we could say, okay, laser has 1, 2 true and 1 found, so which is already pretty good, right? And then we can run it and then see what it computes for us in terms of matches. So how many do we get back? So this time it's a bit more, 19.
19.
Right, but that's only from the first row, right? So and then we could say, okay, which one of those do we want to use? And then we could continue from here, right? So there's lots of ones with a C in there, for instance. So we could pick one with a C in the middle also, so that covers a few of them. Or with a T, actually. T sounds actually also good, right? So, and so we could later, right? So if we say this is a T, right?
Yeah.
And so on, right? So actually later would not work because that's the R is wrong, but you get the idea, right? So you would basically can pick one and then take it from there to the next step.
Yeah, exactly.
But 19 on row 2 is actually quite nice from 12,000, right?
Definitely is.
Already. And before we run out of time, one thing that I also want to show you is basically what these graphs look like in Bloom. So I just need to pull the password real quickly. A second. So this model actually looks like a very dense supernode thing, as you can imagine. But the other model has a little bit more structure in there, right? So we just open here for the Bloom. We have character and word. So for instance, and word is actually indexed. So for instance, if we used our elder, which it automatically finds because there's an index for it, right? We can use our word and then basically character. And then we can also say which other characters basically, which other words share characters with elder basically, right? So this would be something that we would see. So we have all these words.
So yellow nodes are words.
Yellow nodes are words, right? 999 words basically. And so I think it can select elder here, right? So we can actually drag out elder. So this is our starting word, and this is basically only one character, which is basically L, right? So and all these other words here,
These are all the other words that also an L, yes.
Have L's as well, right? So we could actually also increase the node limit to 10,000 or so, and see what my computer would do.
Well, if we lose Michael in a second.
I have another idea. What we could do is we could actually say, if you would spell it out individually, right? So we have E. Let me just clear scene. E. Does it do E? Should be actually. Care E. Why doesn't it do this? Didn't I create an?
Did you
Schema. There's a character on character. There's a constraint there. So actually, or it could be because it's only a single character that it doesn't. But we can actually cheat a little bit. We just let it give us all the characters, and then we can just select the ones that we need. So we said elder, right? So see, there's the L.
There's
the E.
the E, yeah. To the left
There's
is
the
the R.
Q O D E L D. Oh no! I clicked somewhere else. Great.
That's the E to the right of your mouse.
Yeah, and there was because we have the double L, right? So we have it unselected them again. That's present. So this is the D. So we can basically dismiss the other nodes. So and then fit to selection. I think we can also just relay out it. And then we can actually say reveal relationships or Oh no, this in the next node Bloom version. I think this is Bloom. No, that's Bloom 2. Actually, this should have. Or does it only reveal relationships between? It's interesting. I thought it reveals relationships between arbitrary things as well. So we can also find the shortest path between two nodes and then basically take it from there. But it's a little bit unfortunate. I thought we can just select the nodes and show us all the words between those four.
I see now. I know what you mean. Yeah, okay.
So there's a new feature coming in Bloom that allows us something like this ourselves. But it's not in the current version yet. So
it's powerful just to show one random connection here.
Yeah, so this is kind of just shows one shortest path basically as such. But what I wanted to have is actually between those four nodes basically show us the words. So which hasn't worked out so well. But you can basically use this to explore the data visually if you want to, right? So we can take any word like what if we have crash, and then say okay, from this crash, which characters are there, and then come on, and then you could basically select other things here and say expand from these characters, and then you get other 8,000 nodes and so on, right? So that's basically interactive exploration as such. And as a last quick thing is if we look at the second script with the other model, which is a little bit more complex, there it basically says, just show this really quickly. So let's just quickly delete these characters because otherwise we might run out of relationship count. So here, what I do is I split the word by space to characters, create the first character at position so that I can create a special starts relationship, and then create these has relationships. And char at pos has both the index and the character basically. And then I just go over all the other remaining 4 characters, create them, connect them to the word, and then we also create a next relationship between characters as well. Right. So from the previous index -1 characters from index -1 to the current one, and then I execute this in transactions, in multiple transactions, and then hopefully this works. Let's see. 130 labels, and yeah. So this is 5 characters, 26 times, that's 26 times 5, 130, yeah. So that's all our character and position combination, basically. And now we have instead here character at position, which gives us the characters at their position, and then these are connected to words. So if we go back to our queries that we had before, like the one with let's find like here. Our diver again. So we now have, you see the diver, the starts relationship, and then next relationships over here. And each of those has an index and then character basically. And then you can do other kinds of queries on top of this model as well.
Yeah.
One thing that I remember that I've wanted to show earlier is something that's interesting is what is follow frequency. So what's kind of the probability that one character follows another.
Yeah, that's
and
interesting
also
because then I guess the kind of word you're looking for might be you get another tip of what word to put in next.
Exactly, and that's something that you can do on top of this next relationship, where you say I have a character at a position here and a character at a position here, and then you basically return c.char c1 and c2 count star. So how frequently does this one character follow the other one, basically, right?
C1, you need to return C1.
C1, yeah. Thank you. So what's a little bit weird, I saw this just before the call, for the live stream, that this all returns 4, which probably is related to that within those. So you see that some have 3 to 1. So that's always per word, kind of. That's the maximum count somehow per word that this happens. So actually, I need to look at the model, what I've got wrong here. It should actually have higher count. So it could be actually that we should not return the count, but the sum of the in degree. So how often basically did this character appear in a word, and how often did this other character appear in a word? And then basically say the sum of the two is basically how frequent they, how often did it appear at this position basically in a word, right? So if you say size of C1 plus size of C2, and then sum this up or something like this. So this is more realistic, right? So, and then as follow, order by follow descending. So one captures the structure, and the other one captures kind of how often did the structure basically being used in a way, right? So AE is obviously something relatively frequent. SE is also really frequent, and so on. So you see kind of what's frequent, but also what's kind of RA is also frequent, right? But if you order this ascending, so what are rare? JJ. So all the doubles.
Yeah.
Especially, okay. I mean, something like Bloom double O is pretty, or EE double E is not so infrequent, right? But JJ is probably.
Yeah, that's also common. Yeah.
But it must somewhere it has to be. So
yeah, it must be 292 words. Yeah.
Somewhere it has to be, right? BJ, VH, XF. XF is.
Yeah. But there are 250.
This is also something that you can use basically as well in the analysis, what character are likely to come next, right? And less likely. So when you pick your words, but because the solver already captures the structure of the labeled data, to say so, right? So of all the possibilities, the solver actually already takes this into account, right? So because that's already in the real data. So this would only be if you don't have the real data, then something like follow frequencies and character frequencies would be useful for picking things, right? So then that.
Well, it kind of gives a tip, right? I mean, like when we were doing the Wordle earlier, we know that it ended with DER, and then we kind of like, okay, what? I mean, we could have looked at the list, but then also this would give us now a hint. Okay, we know DER, so what word, what character before a D is likely to appear, and then we can say, okay,
exactly. So we could say exactly what's most likely before a D. So for instance, if you say this has char D, right? then we see PD. Oh, sorry, this is ascending. We want to look at descending. AD, ED. Okay, LD is down here.
Down here, but we could
So
have.
we would
I
have
guess,
probably not picked it, right? But
although
but you're right, right? So
yeah,
that's
yeah. Yeah. Although we know
yeah.
that the O was already out, so the S was
Yeah,
also
and
out.
exactly
So probably,
that's a good point because you can
yeah,
filter out the ones that are already disproven.
yeah,
So perhaps actually L would have been in there, right? And
yeah.
I think the tricky part was the double E
It's double E
basically,
for sure. Yeah,
right?
yeah.
So which is really interesting. So that's also something that you can actually check is how many words are there with double, right? So where we can say where C1 equals C1 dot character equals C2 dot character, right?
They're on double Ds, and now we check the double Ds.
Yeah, so like what's the frequencies of these, right? So EE is very common, AA, OO, and then it goes down really quickly, right? Even
And this is at any
like
position,
summer.
right? So we check.
No, that's actually next to each other.
So that's next to each
actually
other.
next to each
Okay.
other. But what we were interested in, kind of how many words have the same character basically
Yep.
at a position, right? So we would
This
kind of
because
say,
you are next. So if you remove that,
yeah, exactly. So what we would say is basically a word here.
Yep.
A word has two characters basically where they are the same basically, and then we can basically say what's the how many words are there that have two characters or double characters in there, right? So which is actually count distinct
double the number. Yeah.
So every word has the same.
No, this can't be right.
That's weird.
Yeah.
It can't be right. Where the character. Oh, and C1 is not the same as C2, right? So we don't want to have the same instance of the character at position.
Yes.
But they still should share in character, right? So it's 4,600. So it's actually almost half of them.
Yeah.
Which is, I wouldn't have thought that it's that many. Yeah. Cool. I didn't follow the chat actually. Were there any other questions, Alex, that we?
I didn't see any. Patrick hinted about a time tree, but I don't think a time tree would have made quite a lot of sense in this case. I don't know what you
probably
think.
when you have the multiple entries or something like that, then you could connect them through the multiple tries. I mean, you can connect them kind of going forward or something like that. Right.
Yeah.
Cool. There was something about existing DB auto-pausing. So there's an auto-pausing for free databases after 3 days. And this should only happen when the database is not used. So if you don't use it either with the UI or with a driver, that should actually be solved. There was an issue in between when it didn't capture all the driver interactions, I think. But that should have been solved. So pretty
cool.
Cool, super. So this was fun. And
definitely fun,
by the way, something I wanted to say, you've probably seen my digital display here with the Wordle thing. And actually before the live stream, I was looking for like an existing Wordle thing, but there wasn't any. So I had to in 5 minutes I had to basically sit down and build my own. So that's actually micro-made. That's actually not one from the store from the community, but it's actually one that I actually created as such this time.
People can buy this in the NFT market space of their choosing after the stream.
Exactly. Good point. Good point. Exactly. So actually, if there's you could actually connect this to your real Wordle, and then it could show every day like your actual solution thing from the. That's also
that could be
good use.
Yeah, totally.
Cool. Sounds good. So I really enjoyed this one,
Alex.
Me
too. If you are indeed into NFTs, we did this last week, 2 weeks ago, on the stream. So check out the recap if you want.
Should be the blog post for the NFTs as well. Yeah, here's the blog post for the NFTs.
Michael did an extensive blog post on the topic, so you can have a look at this. Yeah, I think we're done for today. Thank you for watching. I'll put the links and everything else in the description afterwards, and you can check our code, or rather Michael's
Hmm.
code, if you want to try it out yourself. Um, until
And if you
then,
want to see the others, there's also this link. I don't know, Alex, if you shared this with the existing videos in
it's in a playlist,
WordPress.
so you should see. If you watch this on YouTube, you'll see the other videos
Yeah,
in the playlist. Yeah, what I wanted
super.
to say, we will be back next week with it's Valentine's Day, so don't forget, people. If you care, if you don't care, then don't.
Yeah,
But maybe we do something with that theme,
relationship related.
relationship related. Exactly.
Value and
We
relationships.
might cover relationships next week.
Exactly.
Or we do something else and do SQL. No, we don't. So we do relationships for sure. And yeah, thank you for watching. We have a Neo4j Live coming this Thursday, so where we go into the Matrix movie and check the data from the script and see how we can import it into a graph. So I will be joined by Tomasz.
Cool. That's
Looking
a good
forward
one.
to that session. Set the reminders in YouTube. If you enjoyed this session, right, give us a follow on YouTube so you get a reminder when we're on next time.
Yeah.
Yeah, and with that, thank you for watching and have a good rest of your weeks. Take care. Bye.
Yeah. Thank you. Bye bye.
Bye.